Well, welcome. I am Mr. Murphy, and in this video we're going to be looking at the second half of lesson 1.6, and that is to focus on how to solve a system of linear inequalities. Now this is going to be a lot different from the methods that we learned how to solve a system of linear equations. In fact, the only way that we're going to solve a system of linear inequalities right now is by using graphing. And so you want to make sure that your graphing skills are up to par. And you want to make sure too that we're very accurate with these graphs, because that is also going to be important. All right, so let's start though with reviewing what we did in the previous lesson. In the previous lesson, remember, we learned how to solve a system using graphing, substitution, elimination. I want you to take a minute and I want you to solve these two systems using any method of your choice. So why don't you guys go ahead and pause the video and we'll hit play when you're ready to check to see if you've done it correctly. All right, you ready to see if you got the correct answers? Now, I don't have all the work solved for you. If you got these answers wrong, I want you this time to go back through and I want you to see if you can figure out where your mistake was and see if you can get the correct answer after looking at your own work. So we're going to do this one a little bit differently. So the first answer, you should have gotten 1, -2 as your answer. And the second one, you should have gotten no solution. Now, if you got either one of those wrong, please take a minute to pause this video right now and go back and try to figure out your own mistake and make sure that you can get these two correct answers. All right, you got it correct? Let's move on then. All right, so what we're going to be doing is we're going to look at how to solve a system of linear inequalities, like I said earlier, by only graphing. Now, if you notice with these, just like we've looked at some of the other ones in the past, these are in what we call standard form. We could get these to be in slope-intercept form. But even more so than before, I strongly discourage that. When we're working with inequalities, it's a lot different than an equation. Because if I'm trying to solve for y, there's times that I might have to flip the inequality around if you ever multiply or divide by a negative number. And that's hard for people to remember. And that's where a lot of mistakes happen. So just like before, I strongly discourage students from trying to solve these by getting it in slope-intercept form. So if you work with a tutor, and if that's something that they're recommending, it's still possible to do, but make sure that you point out or let them know that I've told you that it's okay to solve this by using the x and y intercepts. So for the first one, x plus y is less than 2. What we're going to do is we're going to use, well, first off, anytime we're solving a system of linear inequalities, it's important to know what type of line we're going to use before we start graphing. So if it's a less than symbol or greater than symbol, we're always going to use a dashed line. So this first one, we're going to use a dashed line when we graph it. Whoops. So let's, like I said, first we're going to find the x and y intercepts. So to find the x-intercept, we'd cover up the y, and we'd get an x-intercept of 2, because there's nothing to solve there. To find the y-intercept, we'd cover up the x. There's nothing to solve there either, it's just y is 2, so we'd get a y-intercept of 2. So we got those graphed here. You see that I did that for you. And then we would connect these with a dashed line. All right, the next step, before we do anything else, and this is where some people forget to do, we're going to find out, because when we graph an inequality, these inequalities, I like to call these boundaries. Because an inequality, so an equation represents all the points only on that line. When we graph an inequality, we're graphing a region, an entire region of the graph. And so we have to shade on one side or the other. So to figure out what side of the line we're going to shade on, because like I said, this is a boundary line. It's like a fence line. And we want to figure out which side of the fence is our property on. Is our property above the line or below the line? I don't know. So how are we going to figure that out? Well, to figure that out, just use a test point. Pick any point not on the line. That's important. You can't pick a point that's on the line. So pick any point not on the line. Now the point 0, 0 oftentimes is a pretty easy point to use. So I'm going to use 0, 0. You notice I just put that in purple there on the graph. I'm going to use 0, 0 as my test point. Okay, now what happens when I put 0, 0 in there? Well, I get 0 plus 0, or just 0 is less than 2. Now, is that true? Is 0 smaller than 2? Yeah, it is. So it's a true statement. So we're going to shade in the region that had that point 0, 0. So what I've just done is I've just said that that side of the fence is my property. And you can think of like a dashed line as kind of like an invisible fence, or maybe even think of it as like a chain link fence where you could see through it, or like an invisible fence line. Now, a anytime we have a less than or equal to or greater than or equal to symbol, which is what we have in the next graph, we're going to use a solid line. So that solid line, that could represent maybe like a privacy fence or just an actual fence that we can see. However you want to, whatever way is easiest for you to look at it. But again, this is going to represent a boundary. So in a second, we're going to put another boundary on here. It's like if we have someone that's come along now and said that, okay, we're going to put our fence through this line. Well, we got to figure out what side is their property and what side is not. So there's going to be a couple parts to this. All right, so just like before, we're going to find the x and y intercepts. So the x-intercept, I'd cover up the y. So if I did that, I would just get x is 6, positive 6. We'd have an x-intercept at 6. To find the y-intercept, I'm going to cover up the x. Now there's more I have to solve here, because then I'd have to take 6 divided by negative 3 to get negative 2. So the y-intercept would be at negative 2. So you can see I've got those 2 points now. Now when we graph these, we're going to use a solid line. And just like before, we're going to use a test point. Now if you notice, 0, 0 is not on the line, so just like before, I can use 0, 0 as my test point. So if I put 0 in there for x and 0 in for y, guess what? It's going to be really easy again. We get the statement 0 is less than 6. Is that true? Is 0 less than 6? Yeah, it is. So we're going to shade everything above the red line. So we're going to shade everything above that. Now if you notice, when I shade above that red line, if I shaded that in blue, yellow and blue make green. So what we have is what's called a feasible region, or a common region. That common region that's in green there, that's going to be the region where any point I pick from that region, if I put it into both inequalities, they would make a true statement in both of those. Now the exception is the points on the blue line, the blue dash line, none of the points on the line would work. But any point within the green region, or any point in the green region and on that red line, would be solutions that would work in both inequalities and make true statements. And if you don't believe me, you could go ahead and take a minute and pause the video, pick any random point in that green section, plug it into both inequalities, and you'd see that it would make a true statement. All right, so that's how you would do solving a system using a system of linear inequalities. All right, so I want you to try this one on your own. So again, these are both in standard form again, so you're going to have to find the x and y intercept. Don't forget 2 things. Check to see what kind of lines you should be using before you start graphing. Will you be using solid or dashed? I have some students that have a really good habit of writing down next to it. The first thing they do is they look at it, is it solid or dashed, and they'll just write down next to it, solid or dashed. So that way they remember when they go to graph it to not just always connect the solid line. Okay. The other thing is make sure that you're checking when to shade. It's not the end of the world if you forget to shade at the very end, but it makes it a lot easier to kind of do a little bit of shading. Or sometimes what students will do is they'll do arrows and point on one side of the line or the other, and then just shade in the common region, whichever method works best for you. But I want you guys to go ahead and pause this video and hit play when you're ready to check to see if you found the correct shaded region. All right, how did you do? Let's check. So your graph should look like this. So the blue line would be that first equation. So again, you'd be using a solid line there. You have an x-intercept of 1 and a y-intercept of positive 3. So then we would connect those again with a solid line. The second graph there would be the red graph, the dashed line. And that one has an x-intercept of negative 4 and a y-intercept of negative 2. So when you graph those two and connect them, and then after doing the blue line, I forgot, you got to shade. So if you test 0, 0 on that first equation, you get the statement 0 is bigger than or equal to 3. That's not true. That's a false statement. So we would have shaded above or to the right of that blue line, however you want to look at it. And then with the dash line, when we get done graphing that one, if you test 0, 0 again in that one, you get another false statement, because if you put 0 in for x and y, you get the statement 0 is less than negative 4. 0 is bigger than negative 4. So we would not shade on the side of the line where 0, 0 would be. We would shade on the other side of the line. So that would be below that red line, that red dashed line. So the region that both of those lines are shaded in common would be that little triangle down here. So that would be your feasible region or your common region. All right, hopefully you did well on that. Let's look at some other systems of linear inequalities. Sometimes we might have more than just 2. In this situation, we have 4 linear inequalities. So some of these might be horizontal and some of these might be vertical lines. So let's graph this first one in blue. So again, we're going to use a solid line here. So I would find the x and y intercepts. So the x-intercept would be at 6, the y-intercept would be at 2, because 6 divided by 3 would be 2. And then we would connect that again with the solid line. And now before we go any further, we want to check to see what side of the line we would shade on. All right, so I would use my test point. Again, we can use 0, 0. Now if you're noticing, when we put 0 and 0 in for x and y, the left side will always end up being 0. So we would get a statement 0 is bigger than or equal to 6. That's a false statement, so we don't want to shade on the side where 0, 0 would be. We would shade above the line on the other side where 0, 0 would not be a point. So right now that is my feasible region. All right, so now I want to go on to the next one. The next one, we're going to find the x and y intercepts again. Now the x-intercept would be 2, but for this one, the y-intercept would be negative 2. Because when you cover up the x, don't accidentally cover up that x minus. That minus is attached to the y. So if we divide both sides by a negative 1, however you want to look at it, you'd end up with y being negative 2 as your y-intercept. So we would connect these with a dashed line. Now again, we need to see what side of the line would we shade on. So basically what we've just done is we're taking that yellow section. I know that my feasible region is going to be somewhere in that yellow region. And that dashed line has just cut it into two parts. We have that really large part, and then we have that smaller piece. So right now I want to figure out, where is my feasible region going to be of those two sections? So if we use, again, our test point, we can always use 0, 0 as long as it's not on the line. If it's on the line, just pick some other point. But we're going to use 0, 0 again. And when we do that, we would get 0 is less than 2. Yeah, that is a true statement. 0 is smaller than 2. So 0, 0 is above that red line. So we're going to shade everything above that red line. So that means that that green section right now is where my feasible region would be. But now we're going to narrow that. It's like we're snipping away. We're going to narrow that down even more. So I want to figure out, of that green section, where's our next part going to be? Well, so x and y. If we just have a plain old x, it's always going to be a vertical line going through where, what is x equal? So we're saying that x is greater than or equal to 0. So if we were to graph the line x equals 0, it'd be a vertical line going through where x is 0. Now this is greater than or equal to 0, so we're going to do a vertical line that's going to be a solid line going through where x is 0. Now for shading for this, you want to just think of it, where is x going to be bigger than 0? To the right or to the left of that line? Well, it's to the right. So we would shade everything to the right of that line, which I'll get to in a minute. But then let's go ahead and do the other one. Y is less than 4. Where y is less than 4, that's going to be a horizontal line. Now if we were to graph the line y equals 4, that's going to be a horizontal line where y is 4. So we draw a line going through where y is 4. But this time it's y is less than 4, so it's going to be a dashed line where y is 4. Now as far as my shaded region, the reason why I held off is just because sometimes it gets to be too much. And so we want to remember that I'm shading to the right of that green line, that vertical line. And then y is less than 4 would be everything where y is below 4. So everything less than 4. So the region that we're going to be shading in, that's going to be our common region, our feasible region, would be that really dark area there, that little shape there in the middle. That's going to be our feasible region. That's any point in that region would be a solution that would work in all 4 inequalities. Okay, so it gets a little trickier here when you have more than one. Let's look at this next one. Now with this next one, I actually, even though it doesn't say it right now, I want you to do this one on your own. Okay, you've had a lot of practice with graphing inequalities, so I want you guys to see if you can figure out where the feasible region, where the common region would be for all 4 of these inequalities. So I want you guys to go ahead and pause this video and hit play when you're ready to check to see if you've done it correctly. All right, well, how did you do? Let's go through this one piece by piece. So for the first inequality, we would have found that you would have had an x-intercept at -1 and a y-intercept at -2, and you should have shaded above that line. Again, you'd use a solid line there. For the next one, the next one I'll do in red. For that one, you'd have an x-intercept at 2 and a y-intercept at 2, and you'd connect those with a dashed line. I want to figure out what side of the dashed line that we'd shade on. If you use a test point of 0, 0, you'd end up with a statement that 0 is greater than 2, which is obviously false, so we're going to shade on the other side, so above the line. So right now, my feasible region would be that green section. But now we have those other 2 inequalities. X is greater than or equal to 0, which would be a solid line going through, a vertical line going through where x is 0. And then we would also have y is greater than or equal to 0. That would also be a solid line going through, but it would be a horizontal line going through where y is 0. Now x is greater than or equal to 0 would be to the right of that line, and y is greater than or equal to 0 would be everything above that purple line. So the common region that would be true for all 4 of those inequalities would be this region here that's really, really darkened. So that would be your answer. So hopefully you got that as your answer for that one. If not, go back and check your work and see if you can figure out where you made your mistake. All right, the next one we're going to be looking at, the last one we're going to be looking at is a system of solving a system of linear inequalities dealing with a story problem. So for these, we're going to have to write our own system of linear inequalities. So this one gets a little trickier. But work with me, and I think we can work on it together, or we'll work through this together. So it says Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs. His goal is to earn at least $200 each week, but he can work a maximum of 20 hours a week. Malcolm must spend at least 5 hours per week walking his neighbor's dogs. For how many hours should Malcolm work at each job to meet his goals? Whew! I have no idea how to do this one. If I just try to stare at that one and read it, I would be lost. So this is why it's important to take it bite by bite, piece by piece, and try to solve it that way. Okay, so the first step is we're going to come up with a system of linear inequalities. Before I can even do that, though, I need to figure out what is my x and y going to be. So we have to define the variables. Now, a little trick to that. Look for the question mark. Because where the question mark is, that's where they're going to ask you to find something. And so that oftentimes is going to indicate what variable, or in this case, variables, we're going to be solving for. So it says, for how many hours should Malcolm work at each job to meet his goals? So he has 2 jobs, if you remember. One job was going to be mowing lawns, and another job was going to be walking dogs. So we're going to use x to represent the number of hours mowing lawns. We're going to use y to represent the number of hours walking dogs. Okay, so our goal is to figure out how many hours he's going to work at each job to meet his goals. Well, we know that he earns, next we're going to come up with our constraints. So another name for a constraint is just those inequalities. So we're going to write those, we're going to focus on those constraints. Now, if you focus on that first sentence or two there, it says that Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs. His goal is to earn at least $20 each week. So that first couple of sentences there is all dealing with dollar amounts, with his income. So that's going to be our first inequality, is dealing with his income. So he's making $20 per hour mowing lawns, $10 per hour walking dogs, and he wants to make at least, okay, so there's your inequality, at least $200 each week. And now that term, at least, means he can make exactly $200 or more. It doesn't want to make less. So at least would be greater than or equal to $200. So that's how we come up with our first constraint, or our first inequality. Now let's look at the next part of that sentence. It says he can work a maximum of 20 hours a week. Now that's all it says. Now some of these, there's going to be parts that are going to be implied, and you're going to have to kind of read between the lines and understand what they're saying. So if it says he can work a maximum of 20 hours per week, that means between mowing lawns and walking dogs, the most he can work is 20 hours. So the way that we could set that up is we would say that x plus y has got to be less than or equal to 20. Because if he can work a maximum, that means he can't work any more than 20. 20 is the most. 20 is the cap. So we would say x plus y is less than or equal to 20. Now we have also what's called this next one says he must spend at least 5 hours per week walking his dogs. Now that one is going to be one of those where we're going to have just, in this case, a horizontal line. Well, we wouldn't know that yet because we haven't graphed it yet. But it says at least 5 hours walking his dogs. It doesn't say anything about how many hours he's got to do mowing lawns, but we just know that he's got to work at least 5 hours walking dogs. So y has got to be greater than or equal to 5. Now it doesn't say anything about x. It doesn't say anything about how many hours he's got to work mowing lawns. So we just have to know that there's no such thing as a negative amount of hours. And so x has got to be greater than or equal to 0. Okay, so that's kind of like a common sense inequality. Well, let's go ahead and graph these. So when we graph these, again, x has to be greater than or equal to 0. Essentially, y is also going to be bigger than 0. So we know that there's not going to be anything negative here. So we're just going to focus on quadrant 1. Okay, so all of our answers are going to be in quadrant 1. So we don't have any negative x and no negative y's. Okay, so let's go ahead and graph that first inequality. So if I were to graph that one, I would first find your x and y intercepts. So to find my x-intercept, I would divide both sides by 20, so I'd get an x-intercept of 10. To find my y-intercept, I divide both sides by 10. I get a y-intercept of 20. So we get an x-intercept of 10, y-intercept of 20. We connect those with a solid line, just like I've done. And now we're going to do the same thing with the next inequality. So we're going to cover up the x, or cover up the y first to find the x-intercept, and then cover up the x to find the y-intercept. Notice with both of those we would get intercepts of 20. Oh, and by the way, I forgot the shading. So if we were to test on that last one, if we put 0, 0 in there, you'd get 0 is greater than 200, clearly a false statement, so we'd shade above that line. Okay, and then we would have our second graph, though, we would graph that one, and we would have our x and y intercepts both being 20. Now let's figure out where we would shade on that one so we don't forget. If I put 0 in there for x and y, I'd get 0 is less than or equal to 20. That's a true statement. Okay, so we would shade below that line. So right now, that little triangle piece is my common region. Now let's do this last one. Y has got to be greater than or equal to 5. Because remember, he has to work at least 5 hours walking dogs. So I'm going to draw a horizontal line going through where y is 5. Now, on this graph, we just have to estimate it. It's okay. 5 would be between 4 and 6, halfway between 4 and 6. So we'd have a solid line there. Now think about it. What side would we shade on if it's above, or if it's greater than? Just gave it away. If it's greater than, we're going to shade above the line. So that's the side of the line that we would shade on. So you can see there that that gray area is our common region, or our feasible region. So any point inside of there would make a true statement. Okay, so our solution to this would be, we could pick any point inside of there, and that would be our answer. Okay. Well, that's it. That is the end of our lesson. So this marks the end of Unit 1. So hopefully the second part of this lesson, as far as how to graph a system of linear inequalities, made sense to you. And with that, good luck now as you work on your homework.